Hello, friends. Here for another session, and this is a follow-up to our first and most basic null significance test called the z-test, which is a test of a sample mean in comparison to population mean when the population standard deviation is known. So we're going to look at a natural follow-up or even a standalone thing that one can do that is different from the null hypothesis significance test. And this confidence interval, and it asks the question, given known sampling error, what is the range of values around the sample mean that would be a plausible representation of the population mean? So it creates, rather than a binary decision about yes or no, sample mean is like the population mean, or no, it is unlike the population, which is the binary test for null hypothesis significance testing. It simply gives a descriptive range of values around the sample mean. So let's go, I believe, backwards for a minute to put this into perspective with the z-test. So in the z-test, we have what's a point estimate. That's our sample mean. That is the value that we have obtained that is some kind of estimate of population value, the mean, usually the mean. And we test a hypothesis that this is our hypothesis that our sample mean deviates from the population mean, x bar minus mu, only within standard error, as expected by random chance alone. Actually, I shouldn't have said only within one standard error, but only within a range of error would be expected by random chance alone. And so we decide how much error we're going to define as within error. Or again, probably shouldn't have written standard there, within expected or tolerable error. So some people even about tolerance. And we do that by setting an alpha level. 1 minus alpha is the amount of the distribution we consider. So if alpha is 0.05, then 1 minus alpha is 0.95. So we consider, by tradition, that 5% of the distribution is sample means within a range of 95% of the normal distribution. We're going to consider probable, likely due to chance, not unlikely due to chance. And alpha is distribution that we consider outside the range of probability. Unlikely due to chance, we say this is a fringe far enough away from the bulk of the distribution that we're going to reject the null hypothesis that it is a representation of the population, and we're going to ascribe it to something else, in addition to sampling error, which always comes in. But we're going to say this has some distinguishing characteristic. We believe that it does. And we do that by calculating the z value because that's what we can put to the, we can relate to the probabilities under the normal distribution so that we have a probability value. So what's under chance? It's going to be our alpha. It's the region in the far tails of the normal distribution. So the normal distribution, I think on the next slide, has two tails and its body. And these far tails are where values rarely, and we're only going to be talking about what's called a two-tailed test, a non-directional hypothesis or a non-directional test, which is where we're just looking for, does our value equal or not equal the expected value for the population? We're not bigger, is it less than? We're just saying, is it one way or another? Is it different? And we're going to get to two-tailed tests pretty soon, but we're going to kind of take it one step at a time. So imagine that prepared to say that if we have a sample mean somewhere in the region of the 95% of scores that are spread around mu, the population mean, I'm going to say that we're going to be okay with saying that those are likely due to chance. We want to be safe. We don't want to say that they have to be, that they can be 10, 20% of scores outside the boundaries. We want to be fairly conservative. So they have to be 95% of the scores in the body. And if we think that the sample, if we find that a sample mean is outside of this 5% middle region in one of the tails, we're going to say that's unlikely due to chance. So that's alpha of 0.05, 1 minus 90%, or 1 minus 0.95. And we relate that to it. We have the sample mean. This is a case with z-scores. We know about both mu and sigma, the population parameters. We can calculate the score for the sample using the mu and sigma. And the z-score can relate to, it shouldn't be an imposter, can relate to a percentile or the proportion of the normal distribution that will fall below it. And so if we've alpha of 0.95, and then we obtain the z-score related to our sample, we can determine whether or not our sample mean falls within the body or outside the body. Now, so this is 95% here that I've got in the middle of this body. These together, each of the distribution, total 5% outside the probable region. Total, this has a probability above it of 0.975, and this has a probability below it of 0.9. So altogether, you only get 95% within your probable range if in fact you only have 0.02 in these tails. So that's why you talk about z is the probability of 1 minus alpha, but alpha over 2, because it's actually split between the two tails. And that is, those are called the critical region. And the z that corresponds to that probability is called a critical z. And it's positive or negative. So it can be either the z that is beyond probability of 0.975 to 2.5% of values, or it can be the negative z that corresponds to below 9.5. So it's actually at the 0.025 percentile. And it, which it won't be in your book because your book doesn't have any scores. But it is the positive or the corresponding positive or corresponding negative value. So it's minus 1.96. And the 5% for the alpha is divided over these two regions. Okay, so that's the point estimate. That was getting your z-score as it relates to a single point. And likelihood to an exact point of a sample mean occurring by random chance. And as a numerical example of that, Dr. Mendez, he did in class, he knows that the scores of Ames Math and a charter school system are normally distributed with a mean of 250 and 50. He had 36 kids. The sample mean was 265. His hypotheses, his null hypothesis, that the population mean minus the mean represented by his sample, the population mean represented by his sample, is 0. There's no difference between the population mean and whatever is represented by his sample. And the alternative is that there is some difference. He knows mu and sigma, and in that case, he can use a z-test. Otherwise, he has to use that we'll be covering soon. He set a priori an alpha of 0.05, and he finds that critical z, which we did just previously, of plus or minus 1.96. So his z for this sample has to be those values in order to reject the null hypothesis significance test. So here's his mean. Here's his standard error of the mean derived as population sigma, or standard deviation, divided by the square root of his 36 sample size. This is the value that we got for the error of the mean. Put that into this formula. You get a difference of 15 over 8.33, and he has a score of 1.80, which you relate to this plus or minus 1.96. It does not exceed the critical value of plus or minus 1.96, so you retain the null hypothesis, and you say the difference between the sample mean and the population are not unlikely due to chance, or are likely due to chance, or not statistically significant. So say that instead, we just want to estimate the span of values around our mean that we'd consider likely due to chance. We don't want to test a null hypothesis. We just want to have a descriptive result. There's no particular rule. It's a descriptive method. And a lot of people just think that this business of retaining on the basis of a single point value doesn't seriously take into consideration what probability means. That because it ends up, you're talking about likelihood and expectations and the fact that there's random chance, but it's very binary decision, which is all anybody pays attention to in the end. It's what you get published based on. And a lot of people think that that's inappropriate for the field and don't want to do that. So this is an alternative where you can actually just look at this range around your sample mean, and you can say yourself, you can say, that's an interesting range of values, that's a large range of values. If it's a large range of values, it probably do something either about the amount of random error or about the sample size. We're going to get into all of that, but for now, we're just going to see the formula for doing it. Also, one thing that people often simplify this to is that if the confidence interval overlaps with the value under the population mean, the population mean, I don't quite know why I said likely values, just if it range includes the value of the population mean, it suggests that that your sample mean and the population are not different, and that any discrepancy is within sampling error. So it will replicate if you set it up with it's called a 95% confidence interval, and your alpha is 1 minus 95%, you'll have an exact correspondence. The breadth of your confidence interval, whether it will include the population mean or not, you reject a null hypothesis. That again is, it's not very interesting, but you'll see it frequently and from experience as we go along. In fact, we'll see it in just a second. So here's the formula. Formula looks a little bit ugly. It's really not. You name the type of confidence interval by 1 minus alpha. If you decided on an alpha of 0.05, then it's a 95% confidence interval. And it's calculated as the sample mean plus or minus the z that corresponds to 1 minus your alpha level over 2 times the square of the mean. You may note that this does not contain the population mean value. It does not involve mu. So that's interesting. It is not a description that relates to the population mean. So looking at breaking down a little bit more, okay, this is your mean, simple. This term here is like, it's what you've already seen. It's, so alpha 0.05, 0.05 divided by 2, 0.025. 1 minus 0.025, 0.975, which is this, oops. Critical region, okay? And it's minus, there's the plus or minus in this formula because same reason, it's two-sided. Confidence are pretty much always two-sided. And so this is going to give you this Z for a alpha of 0.05 or a 95% interval. This Z will correspond to the Z in an alpha 0.05 Z-test, or minus 1.96. And you multiply that by the standard error. So we do this with Dr. We have the mean plus or minus. We're going to put in 1.96, which is 0.975. The Z to that, which is 1.96. Multiply that value, 1.96, times 8.33, which is our term from before. And then we're going to do two things. It's plus or minus. So we're going to add the value of this product to 265, and we're going to subtract it. So we're going to have two ends. That's why it's called an interval. Two ends, a positive end, a lower end, usually called a lower end of a confidence interval, and a upper end. So the end of the confidence interval is 281.33, and the lower end is 248.67. And you write it like this: 5 CI, and then the I've got this as upper or and then lower. I'd check somewhere and see whether you're really supposed to do lower and then upper, but that's the general rule. And you see the interpretation is most important. And the interpretation would be that 95% of random samples drawn from the population represented by will have a mean mass score on Ames between approximately 249 and 281. Note again, it doesn't say anything about the population mean. Also, it's interpretable as a range of values on the scale of the original variable. It tells you some, if those numbers made sense, then 249 to 281, you'd know something about, well, so we know that the standard deviation, I believe, is, I think it was 50 points. So the upper range is, the population mean was 250. So the upper range is not 250, 30 points, a little bit more than half a standard deviation, which isn't a great deal above this mean. But there are ways that you can interpret this, all of which are descriptive. You note that the confidence interval includes the 150, which is the population mean, the value under the null hypothesis. So you can make the deduction that you would also have rejected the null hypothesis if the null hypothesis were at the same alpha level. That's all for confidence intervals for now. You can do confidence intervals for other tests, and you can also do confidence intervals for other alpha levels or ranges of probability. But we're going to save that. I hope that you got something out of this, and see you next production.